Welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 8th, 2025. We're looking at an ICLR conference paper from a few months ago, January 22nd, 2025, titled The Complexity of Two-Team Polymatrix Games with Independent Adversaries. This paper investigates how hard it is for computers to find a Nash equilibrium, a stable game state where no player gains by changing strategy solo. It focuses on two-team, zero-sum polymatrix games, so one team's gain is the other's loss, and payoffs come from pairwise interactions, where one team has uncoordinated, independent adversaries. The core finding is that this problem is CLS hard, meaning it's computationally very tough. Okay, so to understand the impact of this CLS hardness, Figure 1 provides a useful map of related complexity classes. At the bottom, there's P. These are problems solvable efficiently in polynomial time. The class CLS, which this research shows the specific two-team polymatrix game problem is hard for, contains P. Then, CLS itself sits within both PLS or polynomial local search and PPAD, which is polynomial parity arguments on directed graphs. All these complexity classes are part of TFNP, total function non-deterministic polynomial time, a family of problems always possessing a solution, even if that solution is hard to find. Alright, so building on that complexity landscape, Figure 2 provides a visual intuition for Karush-Kuhn-Tucker points, often called KKT points. These Karush-Kuhn-Tucker points are essentially conditions that solutions must satisfy in certain optimization problems. The figure shows a constrained space, a box, with variables x and y. We see different points plotted. The green ones are valid Karush-Kuhn-Tucker points, while the red ones are not. The arrows represent gradients, which indicate the direction of steepest change. This visualization is key because the paper's hardness proof relies on finding these Karush-Kuhn-Tucker points within a min-max problem, a problem where one tries to minimize a value while an opponent simultaneously tries to maximize it. So, tying this all together, the paper's method of using those Karush-Kuhn-Tucker points in min-max problems leads to a significant conclusion. It establishes that finding a Nash equilibrium in these two-team polymatrix games with independent adversaries is CLS complete. This CLS completeness, meaning it's not only in the CLS complexity class, but is also one of the hardest problems within that class, signifies the problem is computationally very tough, even with simple game setups. This insight also extends to the difficulty of optimizing certain min-max problems. Well, that's our look at this research. Thanks for joining me, Alex, on the AI Research Roundup.